All right. Hello, everybody. So we today we continue on our regular schedule, and so the first let me get my notes. And so where we stopped it was 3 weeks ago. We wanted to know what is the equivalent GLV equivalent K theory of the projective space POV. Wanted to know what this is, and we almost computed it, but since it was 3 weeks ago, maybe I should remind you how this computation goes. So the first step, and this is that the projective space we can write as a quotient. You take V, take out the origin, and mod out by GL1. And so we discussed there's a general principle that if I have a quotient, so then quotient by some group. So if I'm taking some like a quotient by some group G. So if I have a free action on some group G on some Y, then the equivalent K theory of Y is the same as the ordinary K theory of the quotient. And that if they have more groups that have more groups that go along for the right, you have there's a similar statement. And so in this situation means that this object is the same as GLV cross GL1 equivalent K theory of V, take out the origin, right? Where GL1 acts by scalars here, so it's really the center of this group, sits in the center of this group. Incidentally, there's an exercise, so maybe an exercise is from this to deduce that if I want the G equivalent K theory of some G mod H, some homogeneous space cross X, that is the same as KH equivalent theory of X. So that's this. And so now we look at this, and we discussed that we can consider for this, we can consider the equivalent embedding. So there is a maybe iota map from just 0 means set 0, mapping into V, embedding by 0. And then given a closed embedding, we discussed there is a long exact sequence in K series, which takes the form that if I take the K, so maybe you call this whole group, let's call this whole group G. So the way the long exact sequence goes is that I have G equivalent K theory of the open. So I take V, this would be, and then the whole thing, this map is by restriction. And then there is this map, which is, you have a equivalent shift on 0, and you just push it forward, extend by 0. So this is maybe let iota push forward of K G of just point, right? And so in principle, there is a K1 of the open, which we're not going to need this. In general, we won't need higher groups for a long time. And so this is what we want, is the co-kernel of this map. Okay. Now, what is this? So if I have, so we want to know what is this state. step here. And so if I have, so in particular, so this is, what does it mean? I study G covariant Casey on a vector space. Means I study modules over polynomials, but this module, since I study, in particular, I have scalars that act by dilation, and so in particular these are graded. So this is about graded. This is about graded rings over polynomials. So very easy to see that any graded module over polynomial, there's a graded module of polynomials. If you have a graded module of polynomials, very easy to see that this is going to have a finite free resolution. Well, namely because if I write some resolution, then by Hilbert-Syzygy theorem, the last term in that resolution would be locally free. But if it's locally free and equivariant, then it means it's just free, because it means if it's free in some neighborhood of zero, the equivariant with respect to dilation, that means it's free. And so this has free resolution. Another way of saying this is that if I consider the other map, so there is also projection map, maybe call it pi here, just projection. Then the other map, the pullback, with respect to pi, that is just an isomorphism. Is an isomorphism. Sorry, this is not how I spell is an isomorphism. So this map is an isomorphism. I apologize. Isomorphism. Okay. And so okay, so that means we need to compute. So what we need to compute is, let me get a drink of tea. But what we know is that both terms here, they're both isomorphic. This is just representation. This is representation ring of G, and this is representation ring of G. And all we need to know is what is the resolution of, we need to compute equivariant resolution of the image of the generator here is the structure shape of the origin. So this is, we think of this in the case here to know what this map is. All right, so this may be, and this is the subject of Kazul resolution. This is where we stopped. This is where we stopped last time. And so let me explain how this goes. So in general, suppose I have so my group G contains the maximal torus. T, which is diagonal matrices. And so this is generally very useful to think about how resolutions, to talk about resolutions of T covariant resolutions. So in particular, any G covariant resolution is T covariant resolution. So suppose we're in 2 dimensions. So let's just start by way of an example. So we've taken, let's say, dimension D is 2, and we need to resolve some module, not just this, but some T covariant module. Well, what's the typical T covariant module? Well, a typical T covariant module is just a quotient by some ideal, and a torus invariant ideal is like a partition. So this is if I take if I take all monomials that lie outside of a partition, so and this defines for me, this is a torus invariant. If you think of this as a list of all monomials, so kind of, 1, x1, x2, x1 squared, and so on. So all monomials in here, they form an ideal in, well, let's say cx1, x2. Doesn't matter what the field is. And so then if I want to know the resolution of the quotient by this ideal, so if I take O mod, so this, let's call this ring R. So then, so if I want to know this R mod I, or maybe let's not see, I have R denoting something else. Let's not call it R. If I want to know the my ring modulo this ideal, and how does the resolution go? Well, first there's a generator, right? So the generator sits here. That generates the whole ring. So this is my ring. Maybe let's call this ring R, because it's otherwise we'll just have to carry this along too much. So we'll just call this ring R. And so there's this R times this generator. And then what's the kernel? The kernel are the generators of the ideal. And so where sit the generators of the ideal? Well, the generators of the ideal, they clearly sit here. So this is where this is and these are the, and so this would be direct sum. There's the kernel, which is direct sum of R times this monomials. And then, so what does this generate? This generates, so every one of them generates, this is, every one of these terms the monomials in it look like that. Sorry, this is not what I wanted to do. And so we see that, of course, here's a big kernel, because everything like this box here, for instance, if I take this box here, that is covered twice, and then therefore everything beyond it, and so that is also covered twice, and that is also covered twice. And in fact, the kernel is precisely generated by that. That is the kernel. And then it's 0. Right? So in particular, we check Hilbert's syzygy theorem that indeed the third term of my resolution is just free. Like I said 5 minutes ago, if I have, in general, Hilbert's syzygy theorem says that whatever nth term of the resolution is going to be locally free. But in equivalent situations, since I'm equivalent with respect to dilation, if something is locally free, it's just free. So that's what it looks like. And now we go. So this is useful. If you've never seen this, it's useful to remember, because you're gonna need some computation like that later in the course. So let's just think about 3. And so what's the actual ideal we need to resolve? So the actual module we need to resolve is the structure sheaf of the origin. Maybe I'll write it here. And what is the structure sheaf of the origin? Structure sheaf of the origin is my whole ring modulo the maximal ideal. So maximal ideal generated by x1, x2, x3. Right, and so this picture, which I which I drew in 2 dimensions, this will look like, so if I have my coordinate axis maybe say in gray, then what I need to resolve is just one single box. So maybe put it in blue. Okay. So, all right. And so where would be the generators of the ideal? Well, this is clear. So then we have to take this picture. Paste. And so then the generators of the ideal would be these boxes. Okay. And so this means this would be direct sum R times just each xi. Okay. Where would be this? What would be relations between this? Well, again, the analogy we just discussed makes it clear where the relations are. So the relations would be these boxes. Okay. And so that means get direct sum R, so this may be I less than J, xi, xj. And then the last piece is that, so this is we're in 1 dimension more, so it's going to be, the resolution is going to be 1 term longer. So this is going to be like that. So there will be 1 more box, which we'll put it on blue. Okay, it looks like a Rubik's Cube, and except it's a kind of simplified Rubik's Cube. It's R, x1, x2, x3. And that's the resolution. And this is a resolution, is a torus equivalent resolution. It's clear how to make it GL equivalent resolution. We just take, well, the J equivalent resolution, the way it's written is you take, this is, sorry, I apologize. This is my R, and it maps to structure shift of disorder. So R mod the ideal of x1, x2, x3. And so in the J equivalent way, it's the structure shift of my variety V. What is this representation? That's just the defining representation. I'll write it as V odd times, or rather the dual. This is the dual of the defining, because these are linear functions on V, so this is the dual of defining representation. That, and the next term is, well, this looks like the exterior square of the defining representation. Tensor V. And then here is the exterior cube of the defining representation, of the dual of the defining representation. Tensor V. That is resolution. And now how to write the differential in a manifested GL invariant way. So we have some differential G. And how we're going to write that differential. So to write it in a manifestly equivalent way, you know, I do it like this. We take summation over I, and now in the first term in the exterior wedge, I'll write it as a d by dxi, but this means as a in the odd sense, means if I have this is in the odd sense. This is like the functions on the superspace. And so when you differentiate the function on superspace, you first use commutative relation to, if you have that variable, you put it first and you remove it. And if you don't have that variable, the result is 0. So this guy's anti-commute, the anti-commute in particular, anti-commute. So d by dxi square equals 0, and d by dxi dxj equals minus the other way around. And so now this acts on this factor, and it acts on this other factor. Okay, that's because of this relation. This squares to 0, and it gets what I want. This is called Kazul. So this is called Kazul resolution. And now finally we wrote it in so this is in a GL. So this is we wrote it so far in for GLV equivalent way, but we had GLV cross this extra GL1. And so then if I have that extra GL1, well, how does this act? So X sits in this GL1. And so it acts by, so in principle acts by S to the minus K on the, because it's the center on the dual space, it acts by -1, and so on the kth exterior part of the dual space, it acts like this. But since it acts by a scalar, we might as well move that scalar to the other side of the tensor product. So I'll just write it here by S -1, S -2, S -3. And so when we think of this identification upon, if we unravel the identification upon the identification that if I want the kg of v minus 0, this is the same as kg mod GL1 of PV. This variable, so this is a variable here, so it has to be here. This S, again, this is easy to convince yourself. It's going to be a line bundle here, and the function is going to be O of 1. So you can check that. It's a good thing. It's a good exercise to check this. And so this means that we get this. So this means we get this relation. With this relation, I can write S otherwise, so that we get. So the conclusion is that this, well, we computed this. This is a co-kernel. So result. This is the resolution, and this resolution computes what is this. The co-kernel multiplication by that is this map, and so the result is K theory of GLV of POV. That is what? That is, you take it's generated by take a, well, maybe I'll write it like this. You take the GLV equivalent K theory of a point, and you adjoin one variable together with inverse. So this is for O of 1, which is a line bundle. So its inverse is also in here. And we mod out by the relation that summation of minus S to the power I times L. Well, maybe I'll take the dual of all this whole resolution, so this is going to be Li of the defining representation, that is 0. Okay, so that's the computation. But let's see what does the computation say. So what is this in code? So maybe this is, let's talk about in coordinates. What is it? So this is the representation ring. I.e. Conjugation invariant functions on the group, but conjugation invariant functions on the group, that's the same as functions. These are polynomials in, maybe I take the maximal torus. So any conjugation invariant function is uniquely determined by its restriction to the maximal torus. But since the conjugation invariant, this means invariant, which is symmetric. In the AIs, i.e. W invariant. And so then what is the exterior power of the defining representation? This is the trace of this matrix in this representation. Well, what is this? This is the i's exterior power of a defining representation. This is the sum of all. Well, this is all right. It looks like this. It has the bases, which are i-element subset of this. Maybe just for the sake of the argument, let's take cube. So this looks like has a basis like a1, a2, a3 plus a1, a2, a4, and so forth. Sum over all 3-element subset. This is called the elementary symmetric functions of this variable a. And so this relation here. So if I want to know, if I want to take this relation. So this is my k GL V of PV. What is this? This is symmetric polynomials. Symmetric polynomials in the AIs adjoin a variable s plus minus 1, and you mod out by relation. Well, if you what does this relation say? This relation says that the product, because this is like a generating function for elementary symmetric functions, so this looks like 1 minus s ai equals 0. So what this means is just really, so this means a union of just toroids, union over R, where you just equate S to be AI inverse. So this is like, for example, so I'm going to write, since I will be, we talk about K-theory, but our immediate goal is to transition to elliptic homology. And when you talk about elliptic curves, you usually imagine elliptic curve to have flat coordinates. You usually think of this as like a quotient of C by a lattice. And so I'm going to use this kind of logarithmic pictures to draw what I want to draw. And so this means if I so let's say you have n equals 2, then so this I have kind of a flat coordinates with coordinates a1 and a2, but I mean everything has to be symmetric in them. And then there's a divisor where a1 equals a2, where something's interesting going to happen. And on that divisor, so what is this? My 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 scheme over there. That's what's it gonna look like. So this is what it sits over. So that's a bit. Okay. So this will look something like that. So this is, we'll remove that to be not confusing. So this is either it doesn't matter if it's, so in logarithmic coordinate means s is either one function or the other function. So this is one, this is one. So this is where s is equal, say, a1 inverse, and like I said, this should be hyperbola, but in logarithmic coordinates I draw it as a and so, and then there is, let me see if I can successfully draw this picture. So maybe I should draw it more like, okay, so all right, the key is maybe draw first the intersection, so then we can draw one and draw the other. So this would be one, and this would be the other, and then they would look like that. So this is where s equals a2 inverse, and this is where s equals a1 inverse. So this is a union of two copies of the torus that is glued over this divisor. So for n is n equals 3, then I similarly gonna have now, well, I will now project, I will now draw a picture modulo the scalars. So this would look like this. So my divisors would look something like this, where a1 equals a2, a2 equals a3, a1 equals a3. And it's a good thing I prepared the picture ahead of time. You can see it here. This is what it's going to look like. So if I already took the quotient module the scalar. So this is in terms of combinatorics, this is just like coordinate planes. So this is fine. If you're happy with this picture, just the coordinate planes in 3 space, and this is, so this is what the combinatorics looks like. But I have a better picture behind me. So you can, all right. So this concludes the computation of grand K-theory of projective space. Now we maybe will draw some lessons from this, and we will draw these lessons already not just only for K-theory but also for elliptic homology. So maybe there's some lessons to draw from this computation, and so the first lesson is that so let me be a little bit ambiguous about my notation. So if I write G, this could mean two different things. This could mean G compact. So in equivalent, in topological situations, we will be doing equivalent elliptic homology in the topological world. In topological situation, you consider compact group actions on topological spaces. Of course, in algebraic geometry, we deal with algebraic groups. So maybe this could be either compact or could be the right algebraic. So this is the split reductive group. And there's one can go between one and the other. And one way to think about, like for example, how to think about the split reductive group. This is the spec of you take the of the algebra of matrix elements. Take endomorphisms D. So this is the algebra. This is Peter Weil will tell you that the completion of this space is the whole L2 on the compact group of. But if you take just the matrix element of finite dimensional representation, they form a finitely generated algebra, and that algebra is the functions on this split reductive group. That's one way to go between back and forth. And so so let me, I think it'll be clear from context which one I mean, but so the first lesson is that if I look at the spectrum. So we were drawing pictures of what the spectrum of K theory look like. So this, if I take the spec of current K theory of X, well, this sits over the spec of a current K theory of a point, right? So this is, so I'll just write it like this, a point. And but this is a spectrum of functions that conjugation invariant. Conjugation invariant functions are the same as the characters of reducible representation. So this is what we have here is really, well, you can think about, so this maybe there's a subset here formed by semi-simple elements. So this is if I look at conjugation invariant function, they only separate semi-simple elements. They don't. If I have a well, so this is really this object looks like you take the semi-simple element and you take the modular conjugation. So this is another way to think about it. You take the maximal torus and you take its modular divided. And so in here, so this different when we had this picture here, there was a certain stratification here, right? So this is there was one stratum generic where all AIs were different. There was some stratus where two AIs came together, and then there was a stratum where all of them came together, and the spectrum of recurrent K theory looked different over the corresponding points. And so what is the stratification? That has a stratification. So in here, let me move this. So in here, we have stratification by stabilizers of the J actions acting on X. If I have an element acting if I have an element acting on topological space, well, I can ask what does this element fix? And so if I vary my point in X, I get different groups as stabilizers of my points. And so this is the certification. So if I vary a point in projective space, a general element in projective space will not be only fixed by a torus. If I take a general element, general point, if it happens to be that so this is no, sorry, I'm saying this incorrectly. Sorry, I apologize. So this is the stratification by by what the fixed laws are like. Like, it's not like, I mean, the projective space is a homogeneous space. Of course, all the stabilizers are the same, but these are the stratification by types. Maybe I'll write by types of fixed laws. Fixed laws. So if I have some element in some piece of the stratification here, what's the put it here. So if I have some element here, some element here, G. So here's this my stratification by types of fixed laws. So then what I have over G, what sits over G, is just really the K-theory of that fixed locus. Right? Now let's see if this is how this works in our example. So in our example, we had.
Sorry, is it like stratification by stabilizer up to conjugation?
I mean, for every element, you can ask, what does it fix? What does it fix? And so then it's up to conjugation. There will be this fixed sets are up to conjugation form different things. And so this is what you take. Right? The stabilizer for projective space, all stabilizers are the same, but a given element fixes different things. Does that make sense? It's really asking what is the fixed locus up to conjugation. And so this is, let's say, let's imagine maybe my let's abbreviate, maybe let's make A1 B1, and so then here is my A2 equals 1, here's A2 equals 3, sorry, A3. And so then my what was my equation? My equation was product of 1 minus SAI equals 0, right? So over generic point, like here, this would look like 1 minus S, 1 minus A2S, and 1 minus A3S, where all these numbers are different, right? So this defines 3 different points. So you get the spectrum of that are 3 points, and that these 3 points, that is the K-theory of the, if I take my projective space P2 and I take the generic element. Right? So if generic element in my group fixes, so generic element in my group sits in some torus, so it is a torus that fixes 3 points in projective space, and this is that. So now what's the opposite situation? The opposite situation where all these guys are the same. And so this means here I get 1 minus S cubed equals 0. So 1 minus S cubed over 0, it's 1 point of length. So 1 point of length 3. And that is, so if I'm over the origin, means I'm fixed. So origin fixes everything, and so this is just the K of P2. And there's an intermediate case where A2 is equal to A3. And so when A2 is equal to A3, here, of course, I'm going to get maybe. So this would be 1 minus S over 1 minus A2 S square. And so this is 1 point of length 1 point, and then another point of length 2. And that is clearly the K-theory of, I take P2, and I take the fixed locus of an element of the form 1, A2, A2. Right? Because this fixed locus, this would be a point in the P1. So So if I take a point in the P1, its case here is going to be a point and another point of length 2. That clear? So in particular, there's some general statement which says that that over generic point. So this is some localization is something much more precise than this. But there are many statements called localization. But one of them is that over generic point we have the K-theory of, so a generic point would be conjugate to a generic point in the maximal torus, and the generic point in the maximal torus generates the torus, and so whatever fixed under generic point of a maximal torus of a generic point is fixed by a whole torus, where T is a maximal torus. So that's to say, if we so what does it mean locable generic point? It means if I extend the coefficient to like a field, so then I'm only seeing that generic point, and then I'm just getting this. Okay. So now, what is this going to look like? So this is what is this going to look like in elliptic homology? And I think it's best pedagogical. It's best if I don't try to first define what elliptic homology is. I think Igor explained the notion of how you get different homology theories from the cobordism, and how in particular you can get elliptic theory choosing a specific genus. And this is one way to define it, and there's other ways to, there's a whole industry how to define it. Maybe it's better to maybe first develop some understanding of what it's going to be. And so what would be the analog of this what would be the analog of this so the first question is what's the base, what's elliptic homology of a point? And so now if I take, so maybe I start with G cross G. What's G over G? G over G is the same as G local systems on a circle, right? So if I have G local system on a circle, that is only determined, I mean, of course, that's only determined by the monodromy. So this is the monodromy. As I go around the circle, I'm going to get some monodromy, but that monodromy is defined up to conjugation, because I have to trivialize it at one point. Okay. And so then it stands to reason. Well, this has to do. This is and this is my. So this is my spectrum. This is my spectrum of G and K0 point. So it stands to reason that if I want to talk about elliptic homology of a point, first of all, we're gonna drop. So we'll just write elliptic. And now let me be careful about compact and not compact. Let's say G compact of a point for a second. And I'm not going to write the spectrum. This will be already a scheme. So this will be a scheme which is already not affine. So this means it's not a spectrum of anything. So it's some scheme. And so we will take that circle and replace it by, so this is maybe, and I also want it over C. So this is the same as G compact local systems on elliptic curve. So far it's purely topological. This is purely topological space. but Narasimhan and Seshadri will tell us that this is, so by Narasimhan and Seshadri, that is the same as direct sums of stable G bundles. So this is for arbitrary surface, but in particular for elliptic curve. So this is kind of silly case, G equals 1 case. It's an interesting theorem for high genus, but it's on an elliptic curve of degree 0, right? And now this is now a complex. This is now a complex elliptic curve. And in fact, for so it's the same. It's a dual abelian variety, but for various compatibilities, it's better to put check here because then you'll see it. I mean, a complex elliptic curve is isomorphic to its dual abelian variety, but it's a bit like saying like a vector space, like every lattice is isomorphic to its dual lattice. It's not exactly, and it's true. It's both true and false. But on an elliptic curve, we don't. So on an elliptic curve, we don't have stable vector bundles of positive we don't have stable vector bundles of rank more than 1. So this is on elliptic curve. This is just, so since G is 1, we get this a direct sum of line bundles of degree 0 up to, well, for let's say if we're interested in GLN, GLN, so then up to permutation, then there's no further construction. And so what this thing is just you take, so maybe more canonically, this is you take E, we copy, so this is this is line bundles of degree 0. Each line bundle of degree 0, it's an element in pick 0 of E check. So, and that is E. So this is one that we want to have E for cohomology, which means we want to recover it's a peak of something else, and so we have to check for something else to be E check. So this is going to be what? This is going to be E to the rank of the group in general, divided by the Weil group. Maybe more canonically, you take E and you tensor it over Z with the co-character lattice of a maximal torus, and you mod it by the Weil group. After all, that is the definition. So this is on the not definition result of some becomes E G of point. Okay. And so then it's clear that this is various subgroups, since we define this to be something that has to do with G bundles on some variety, then various subgroups naturally define subvarieties, right? That's clear? So they will have, in terms of, so this is, we have, so this is, sorry, elliptic, L, H of a point, well, this naturally sits inside L, G of a point. Well, not sits, at least maps. There's a map corresponding to inclusion of a group. And so that this means the stratification we're going to get is now by those subgroups for which have more fixed points somehow, which have some new interesting fixed points. Like for instance, so this is if we take for what's going to be, what do you think is going to be the elliptic homology of elliptic homology GLV equivalent of PV? What's it going to be? This will sit, so this will sit in the product of elliptic homology of GLV. So this is, I'll write it as e to the, let's say, dimension v is n. So e to the n mod Sn cross e. This is where my variables a1 through an lie, and this is where my variable s is. And here I take the union. So this is equals is the union of sets where, well, multiplicatively, I'll just write the same thing. This means group law of that is 1. So it's exactly the same picture. So the picture is exactly the same as behind me, except now it happens not in the, now it happens not in tori, but happens in elliptic curve. Exact same picture. Then so maybe to so what would be, for example, we have in terms of this map here, maybe a good example to think about is that I have a map. So example to think about. So consider the map from GL1 to GL1, which is multiplication by kind of z cubed. Then the kernel of that map is the group of third roots of unity. Then corresponding to that, we have, so in cohomology, so this is equivalent cohomology is, so if I have cohomology is contravariant functor. But since we're taking the spectrum of cohomology, that is covariant. So this is, so LGX is, so this is the spectrum of cohomology. This is covariant with respect to the maps G1 X1 mapping to G2 X2 equivalent maps. So this, right? So this maps preserving action. So in particular, X could be a point, and then we're just talking about group homomorphisms. And so this is the corresponding maps on elliptic homology is going to be E, which is the case. So particular. So in particular, so here E elliptic of, or maybe U1 or J1, whatever. Let's say U1 equivalent homology of a point. That is just E. And so then you get E goes to E. This is multiplication by 3. And so here the kernel are the points of order 3. So sorry. Usually people write on the abelian varieties, usually people write things additively. And so these are the for the if you think of elliptic curve as over C, so as the given by, so if we think of this as C mod Z plus Z tau, this would look like this. So this is 1, this is tau, this would be the points of order 3. So we try to look at like there are points of order 3, like that. And so in particular, so what are these? These are 9 of them. And so they correspond to pairs. So this is really, these points are really, so there's 9 points, they're really pairs of elements. Pairs of commuting elements. Well, it's commutative groups, so in particular, all elements of commute, pairs of commuting elements of mu3. So there's 9 of them, and they correspond to different mu3 bundles over elliptic, over a torus. So this a mu3 bundle over, like a flat G bundle over a torus is just a pair of commuting elements in G.
Sorry,
All
you
right,
said
so this
that elliptic curve is like a spectrum of elliptic cohomology, but elliptic curve is not an affine variety. How could
well, I said from the beginning that this elliptic cohomology, we don't have spectrum. It's just elliptic cohomology is. So elliptic cohomology is a functor that goes from topological spaces to schemes, and that functor is covariant. We already take the spectrum of cohomology.
Okay.
Does that make sense?
Yeah, thank you.
Okay, good. And so so that was kind of lengthy lesson number 1. And so here's lesson number 2. This is about Chern classes. So suppose I have group G, or maybe a group H, and I have so I have some topological space, and I have some P. That would be a principal H bundle for some group, or whatever. It could be G, but it's a principal H bundle. And so usually in topology we say that this is these are classified by maps from X to some BU, or BH rather, but maybe more intrinsically that is just the same as the map from X to the stack point mod H. And so this means there should be a map. If we consider it should be a map, I'll pull back on K theory. That is to say, have a map from the spec of KG. So maybe there's some action of G, and this is a covariant G covariant. And so then you're going to go, where are you going to go? Well, if so, general unravel definition, what does it mean to have a K theory of a stack? Well, that just means you have the quotient stack. That means you have the covariant K theory of the pre-quotient. So this is going to be spec. This is going to be from the spec of K maybe G cross H of point. So that map you can call Chern class. And so for concretely, we will need it for concretely. So concretely, if I have a rank n vector bundle, all vector bundles are complex vector bundles. V on X. then that means gives a map from spec gk of x to just so the k spec g is here to k gln whole point, and we decided these are just symmetric polynomials. In some auxiliary variables, we call them x1 through xn, which are called these are called Chern roots. And so what is this map? This map is just, it's just, so if I consider pullback on functions, it means if I take the kth elementary symmetric function and this, that goes back, pulls back to just kth exterior power of my map. So we've seen this before, right? And so then this means, and it's literally the same. So now it should be for elliptic. Except you go to, except your target is now, except now the target is elliptic homology, GLN. Of a point, which is, we decided this is EN mod S. And so then we say that some collection of vector bundles on V2, whatever, generate K of X. Well, and then you can say, maybe you can say S lambda ring, or with Adam separations. Something, right? So it means you throw in not only means you take this means you take the i's and all the exterior powers. And so we say, so this is generate. So if that is the case, if this means that if you take the spec of kg of x, that actually embeds by this map, there's a map to kg of a point cross the symmetric product. So this product of, it takes symmetric product to the, so this is usually denoted as n of e. So this is rank of which vi of e, if this is an embedding. And then how do you know that something is an embedding? Like for e.g., for instance, e.g., we took O of 1, we take one bundle O of 1, generates K theory of projective space. Maybe it will be confusing. Let's just like that. So, and so how do we know if some collection is generated? So this there's a very general argument for that, and this has to do with under the name of resolution of diagonal. Suppose I take the diagonal x cross x. Then I can ask, what if I can resolve this diagonal by shifts of the form something pulled back from the first factor, outer tensor. So if I have a tensor, if I have a product, then there's notion of outer tensor, means you pull back something from one factor, you tensor with something pulled back from the other factor. And these are in the algebra. If this is the case, then I can think of a diagonal as a correspondence between x cross x. If I pull back to the product, I cross with the diagonal, I push forward. And so if it is the case that, so this of course it's a diagonal, every K-theory class goes back to itself under this operation. But if diagonal is of this form, means every K-theory class is going to be this means this guy's actual span, either side. Just really span. Spans K-theory. So this proves this. If I have a resolution diagonal, it not only proves something generous, but actually gives you something actually spans, because and if I apply this correspondence, I see that everything whatsoever is in the span of Fi's or in the spans of J. And so actually, this strictly speaking applies only compact manifolds. But and so this is how why am I bringing this is that so for instance, this is for the varieties we're going to consider such resolutions of diagonal exist naturally. So for instance, on Pn we have the tautological sequence, namely I take the trivial space, and then here I have the tautological subbundle. So this will be O of -1. So this is if I have a line bundle, the fiber over a line is the line itself. That's O of -1, and so this is like that. And then this is a tautological quotient. And so this is maybe call it sub. And so then on Pn cross Pn, we can take the following thing. We can take the sub from one factor. We can map it to the trivial thing, and then take the quotient to the second factor. So then take this. So maybe not take, consider. So we have this thing, we call it S. S lies in the home from the sub on the first to the quotients on the second. And so sub was O of 1, so this is sub was O of -1, so it's going to be O of 1 outer box with the quotient on the second. And then the diagonal This is exactly where S equals 0, right? Because when the two spaces are the same, the two spaces, well, if it's a, if this, if the map from the one to the quotient by the other is 0, means one is a subset in the other, but they're spaces of the same dimension. So this is exactly that. And so then the Kazul complex of that section, and we discussed Kazul complex in the case of embedding of 0 in a vector space, but there's a Kazul resolution. We will talk about that for embedding of 0 section to any vector bundle. That is resolution of diagonal. And so since that resolution is going to involve only powers of O1, and in fact you can see, well, which powers of O1 is going to involve that. This proves what I claim. And but we often think of maybe the first really interesting variety is the Hilbert scheme. So on the Hilbert scheme, we have C2 maybe endpoints. We also have a tautological sequence. We take, well, it's slightly infinite dimensional, but it somehow doesn't matter. So this means you take all functions on C2, maybe I'll write C1, X2, X2. Then they subject to the quotient. So there's a fiber which is ideal itself, and then there's a quotient. And Cx1, x2 mod I, and that is rank n. And the exact same argument. So now you take ideal one, project to the quotient of the other. It's going to prove for you that this says that this bundle generates K-theory. And so if you want to know what is elliptic covariant K-theory of the Hilbert scheme of points, or elliptic homology of the Hilbert scheme of points, well, maybe hard to describe by equations, but if you want to, know the answer, so then you take the K whatever equivariant. Well, let's do a torus equivariant. T2 equivariant of Hilb C2n. So this would be sitting. So, but the torus is a torus. These two variables here sits inside GL2 and acts, which acts on C2. And so this would be, since this bundle generates, so this will sit inside. What? You take polynomials. You take two copies. So you take my torus T. So this is coordinates T1, T2 cross. You take so there's the. Let me do. Let's do it canonical. So this KGLN over point. This is for this. This is for my tautological bundle. And so this has coordinates. Maybe column A1 through AN, and is defined up to permutation. And so then this thing is a union. Over all fixed points And so now you need to know what are the fixed points of my torus on the Hilbert schema. And this is we've seen some elements of that at the very beginning of the lecture. This corresponds to partitions. So these are partitions lambda of size n. And now, how is my torus acting on the fiber of the tautological bundle? The tautological bundle is precisely this. Well, we've seen this picture before. It's the quotient by this ideal. And so then, I mean, very canonically, the torus T1 and T2 acts, and so maybe this acts on the coordinates, maybe x1, x2, which are in the dual of the space here. And so this acts by the inverse transpose, T1 inverse, T2 inverse. This I'm just being pedantic here. And so this is be saying that these are the weight of the torus action is going to be 1. There will be T1 inverse, T2 inverse, T2 minus 2, and so forth. And so then you say, so the union over this, and then you say, well, you take this are the AIs of the permutation. And this is explicit description of your algebraic variety. If you want to describe it by equation, this will be slightly unpleasant. But if you want to imagine what it is, it's just a union of two-dimensional. So it's again, if you have over in your torus, there's some stratification by some whatever subgroups, that elements that have more fixed points than usual. Over the generic element is just the number of partitions given by this coordinates, and sometimes they come together, and so you get a picture which is much more complicated than this, but you can certainly imagine it would be like. And so now elliptic. So sorry, that was the. Yes, this is the spectrum. Sometimes since we're doing elliptic homology eventually, it's same in elliptic homology. Take T. C to N.
So sorry, actually I didn't understand. So you should have union of some pieces which are labeled by Young diagrams, and they somehow
right. Yeah. So each piece is isomorphic to a torus. And what is this isomorphism? Is that I have for each piece I have n tuple of numbers, namely the weight of the tautological bundle over that fixed point, and I say that n tuple of numbers equals AI. And so previously I had one coordinate S, and that coordinate S took various values like A1 inverse, A2 inverse, and so forth. But now this is or maybe I should call them SI. So to facilitate comparison with what they had before, let's call them SI. So the S1 through Sn modulo S. And these T's are like A's before.
It was
all right.
Okay.
Yeah.
Actually, I still don't really see these pieces which are glued, but.
But do first the example. Do first the exercise do this for the projective space and see if it's exactly the same. So the projective space, I had the union over fixed points, and we took the restriction, the weight. So what was the projective space? We had the union. We had the union over all fixed points, and we took the weight of S at that fixed point.
Yeah, but for projective space, we had like an explicit equation, and here we don't have it. And you say
yes,
that
because it's going to be complicated. If to have an explicit equation, what do you need? You need to take a union. If you want to require the equation for the union, it requires some long Grosvenor bias computation, but you can be done.
Yeah. I mean,
I'm not sure what.
You said that like you have some implicit description.
No, it's explicit description. I mean, explicit. It just tells you what this thing is. Well, I don't know. I think this is it's a good thing to think about if you're uncertain. And so now the third lesson we're about running out of time, but let's just start it. So this lesson number 3 is that, so more generally, so we did projective space, but more generally, suppose I have some vector bundle, maybe call it E, over my space X, over some space X. Then so this is vector bundle. And then what I can do, I can take the projectivization of this vector bundle. So this I can consider kg of the projectivization of this vector bundle. The stills map. This is the spec of that. Well, just let's try the spec. So I was gonna say spec. This is kg. Yeah. And so then exact same argument as we had before. Let me remove this. Exact same argument, same as before, literally same. Same argument as before that says that this is going to be, what's it going to be? It's going to be the K theory of X adjoin one variable S plus minus 1 and mod out by relation, which is summation over I minus S to the I L I. It's literally this. Okay. For instance, we can take, so this is useful. For instance, consider we have this vector bundle E. This is my X. Here sits my E. And we can compactify it by adding the projective space at infinity. So P of E. So this whole variety in total, this whole thing, this would be, the way I define it, this is the projectivization of the trivial bundle over X, or maybe I'll write C, trivial bundle, plus this bundle E. And then I can take the, so consider the Thom space, the bundle E. That is, I take this compactification so Thom space figured in Igor's lecture last time, and I contract the boundaries. So I contract it. So this is like a twisted. So this is, if my bundle was trivial, it would be like suspension. I multiply by a segment, I contract the infinity. So this is like a twisted suspension. Of X. And what do we know about it? So now by this description here, we know what is its K series. So this is kind of the, so this is the K of X direction. And then I add one more variable, maybe call it, which I call S. And then here I have a graph, a variety which looks like this. So I have one factor, which is 1 minus S, or X equals 1. Let's try to make it equals 1. This is for the trivial factor. Trivial factor here. And here I get S equals, maybe call it epsilon I. These are the epsilon I Archer roots. And so then, what does it mean? I take the K-theory or elliptic homology of a pair. Means I consider K-theory classes on the big space that vanish on the subspace. So I'm interested in functions here. So I'm interested in function on this scheme. So I'm interested in one of the functions on the whole thing. That vanish the red part. Well, it's clear that for this, it has, first of all, it's a function on just the copy here, but second, it had to vanish here. So this is really, this is more or less the ideal, and so this is what's it going to be? This is going to be the ideal. Generated by 1 minus epsilon I in K of X. And so there's well, we have to stop now, but there is that ideal is of course just as a sheaf as since it's a principal ideal as sheaf over Kx, this is isomorphic to Kx, and that's the nature of Thom isomorphs. However, not so for elliptic homology. So this is the first place where in elliptic homology something is different. So this is maybe a good place to stop. We'll pick from next time. But this is where we came to the first place where something which is in elliptic homology is not the way it is in K-theory. So in K-theory, again, so in elliptic homology, again, what's it going to be? You have a bunch of, imagine each one of us an elliptic curve, and I'm asking for functions on the union of elliptic curve that vanish on this red part. So that would be, I'd be saying like I want some ideal sheaf, so on elliptic curve, an ideal sheaf of some finite scheme that is not the structure sheaf. Right? That's the whole point. These are all different. These are all different sheets. So that makes well. Okay. Anyway, we've just it's kind of subject slightly endless, and we will continue it next time. But I think it's good we came to some point where you can see the difference between K-theory and elliptic homology. All right, questions? If there's not a single question, then shall I just wish everybody the best and continue next week?